I'm Suarez, and this is Video Lab 1 for Physics 2211. This lab aims to study uniform motion by filming and evaluating an object moving in a straight line at a steady speed. The main objective or the purpose of this lab is to understand computer modeling and motion principles and understand how the second law of motion applies to physics ideas in real-world situations. Another law you should know for this lab is Newton's second law, or better known as the momentum principle, which relates the system and its surroundings to the force, the time, and the acceleration of an object. And specifically, when we relate it to the velocity formulas in this lab, we will know that this F net should be 0 because the object is not accelerating. Therefore, the initial velocity should equal the final velocity. And Newton's second law further explains that if you apply more force to an object, it will accelerate at a higher rate. To preview this lab, we can ask ourselves, is the motion going to be constant? Does it go in a straight line? How will the position versus time graph look? And does the experiment line up with the coding? Well, we know that the motion will be constant because we are applying one constant force and no external forces are acting upon it. It does go in a straight line, specifically in our example, because it is in a track. A position versus time graph will look exactly how it was shown in important principles and will be referred to later on. And the experiment does line up with the code as it is almost symmetrical. The system for this experiment is the object in motion and the applied force, and the surroundings is the friction, the air resistance, and the classroom. The initial conditions are as follows. We have an initial position of 0 and it will displace 1.75 meters to the left because the direction is moving left. The initial velocity is equal to the final velocity because the object starts at rest and the force is applied horizontally. The materials needed for this lab are the camera, a ruler, our object in motion, and the tracker app or a tracking software. The procedure is as follows. We first choose a flat surface to minimize external influences. We then place the object. We set up a camera, and we record the entire motion, ensuring the object stays in frame and is applied a consistent force. Then we measure the distance it traveled, we import this information to a tracker, we calibrate the tracker, we export the data, and we do a code adaptation and a graphical representation. To further understand the tracker app and how we started the experiment, on the left we have a picture and a frame of the video we have. As you can see, we have a metal car on the right, and we are applying a constant force in order for it to travel 1.75 meters to the left. When we look at the bottom right, we can see specifically the way that we have to calibrate the system, which firstly, we have to make sure the axis is parallel with the board that the car is moving through, and then we have to go frame by frame and selecting a point on the card that will go from start to finish and have no errors. And seeing the position versus time graph in the top right, you can see a very constant and straight diagonal line down. And all this information is fed to data that we can later turn into a graph. The code is straightforward and we can mix and match the code and find the outputs we need. Specifically, once we use the data from our tracker, we can change the ball position in the first picture to negative 0.021, and then we can adjust the time it took from 0 to 0.467, and we can make a graph using that and using the velocity that we have found. As you can see from the graphs, the left one is directly from the code, where you can see a perfect scenario where it is a straight diagonal line and the velocity is constant. And if we move this to a code and we compare it to the tracker, we can see that the lines are very identical and only have very minimal differences. For all labs, there are sources of errors and physics errors. Specifically in this lab, we can have measurement accuracies where we don't measure to the specific centimeter or meter how long it traveled. The video analysis can also be slightly different because, as we saw, there is some curves in our graph, which is due to the fact of the frames per second is not calculated accordingly. There is human error that a constant force and friction is present, and model limitations such as we can do this perfectly if there was a place where we had no friction. If we changed or flipped the axes, first of all, flipping axis would invert position and velocity graphs, potentially reversing the perceived direction of motion. And if we do a spatial orientation change, the spatial interpretation of motion changes. For instance, if we go right, it is now left, and the consistencies in our graph would not be equal. It would flip, and the graph would be pointing in different directions. When asking about how many pushes and pulls or forces can be done, my observations align with the computational model that assumes zero net force, which suggests a balanced system, but we do not know exactly how many forces can be acting in order to make a net zero. In our scenario, there is no net force because all of the forces operating on the object are balanced, and the object is likely either at rest or moving at a constant velocity according to Newton's first law of motion. In summary, the results of our car motion experiment and the following construction of a computer model based on physical principles have been noteworthy. The model created can actively and accurately represent the motion, proving how well it can capture underlying dynamics and prove further the second law of motion, and that there is no acceleration in an object that is applied a steady force.